Alright, in this exercise we're going to look at some Laplace transform applications, and rather than being kind of esoteric, you may have seen, not that ordinary differential equations are esoteric, but we're going to apply this to actually what our inputs and outputs may look like. The whole point of Laplace transforms is we can take these differential equations and these discrete inputs and from those derive an analytical solution to what our system will be like. So let's go ahead and let's look at our problems. I have on the left our Laplace Transforms worksheet, our live script, and on the right hand side I have our table from our lesson. So we're going to do, first we're going to look at create a Laplace transform f of s for the following graphical functions in the time domain. So I'm going to go ahead and get out my pen. Let's go ahead and think through this. We have a step function here, and so at time 1 and at time 5 we're going to go up 3, so up 3, and then down 3. So the two things to note here are, first, that if we have a step function, it's going to, or some constant, it's going to be the constant over s, and then if we have some time delay, it's going to be multiplied by e to the negative ts, and we can find that right over here as far as the unit step. Right here is where we're getting this, and then the delay we find down below. So we'll go ahead and this is going to be 3 over s e to the negative s, and this is going to be negative 3, we're stepping down from 3 to 0, e to the negative 5s. So that's our first solution. Let's keep on continuing now. Let's look at B. With this one we have a ramp now, and so we're going to ramp up here, we're going to ramp down, we're going to ramp down, and we're going to ramp up. And the whole thought here is that this would actually go on for infinity unless we canceled out the ramp up here with an equal ramp down. And so when we ramp, we have a slope equal to 1, it's going to be, the slope times 1 over s squared. So here we have a slope, we're rising 5 over 2, so 5 up, 2 over. So the slope of these is going to be 5 halves. Oh, my computer's having a hard time thinking. S squared over 1. And my computer is having a hard time thinking. And so let's just talk about the delay and the other slope. Right here the slope is going to be, slope is equal to 1. Right here slope is equal to 5 halves. And then the delay here, so this is going to be we're going to have 4 elements. I'm going to go ahead and just get rid of these marks. Go ahead and do marks again. We're going to have 4 things. The first is going to be 5 halves 1 over s squared e to the negative 2s. The other one is going to be negative 5 halves 1 over s squared e to the negative 4s. The next one is going to be negative 1 over s squared e to the negative 6s. And the last one is going to be positive 1 over s squared e to the negative 8s. Hopefully that makes sense as far as the ramp. And here we're going to combine them. So we're going to have first, right here, we're going to have a step down, so it's going to be negative 4. I'll just talk it through, just hopefully my computer can handle it. It seems like it's not wanting to talk very well. So negative 4 over s e to the negative s. This is going to be positive 5 e over s e to the negative 4s. And finally we have one other thing. It'll be a slope right here of 1.5, so plus 1.5 over s squared e to the negative 4s. And this is going to be a ramp, that ramp that happens in addition to this jump. So we have 2 things happening at once. Move on to our second equation, or our second problem. Let's talk through these. First, we're going to convert these equations that are in the time domain to the Laplace domain. The first is going to be f of t. is equal to 8t. And so if we think about how that would look, it's going to be a ramp. And so that's going to be 8 times s squared, 8 times 1 over s squared. You can see that right here. We're starting at 0, so there's no time delay. So it's just going to be this equation right here. The second one, we have some unit 2 times the step function t minus 3. So I think about our unit step before. So this is going to be 2 over s, and then e to the negative 3s. So that at 3, that step change will occur. C, we're going to go ahead, we have some 5 times dy dt. So let's look down here, let's look for a differential, here we go. So we'd have df dt is equal to s times the in the Laplace domain of that function, so this would be capital Ys minus f of 0. So I'll go ahead, I'll get out my pen for this one. So it's going to be 5 times s times ys minus y of 0. This is actually going to be 5 over s because it's some constant. And that's going to be equal to, on this side, oh no, we're on this one. So it's going to be equal to, anyway, that is what it is. This is the answer right here. I was overthinking it. We have this one right here. It's going to be the integral. We have this integral function right here. So it's going to be y s over s times 5. Let's go ahead and now 3 is where it gets a little bit interesting. So what I've done is I've actually gone ahead and solved it on paper. So we'll scroll to the top and we'll just discuss what's going on here. So let's make it bigger, make it fill the screen. We'll come in and we'll kind of look at this bit by bit. So 3a says dy dt, or what? Yeah, dy dt is equal to negative k y of t, where k is a constant and y of 0 is 5. So the first thing we'll look at, I have these stars for these Laplace transforms. So df dt is equal to s f of s minus f naught, and y of t is equal to capital Ys. So this derivative on the left-hand side and the right-hand side can be done independently, transforming. So we have s, y of s is minus y naught, which we know is 5, minus ks ys, minus kys, I should say. So if we move the y all the way to the other side, we'd have s plus k is equal to 5, and then all that s plus k times y of s is equal to 5, so we can move that over. 5 over k s plus k is equal to ys. And then we have this relation right here, e to the negative bt is equal to 1 over s plus b. So we can go ahead and convert that. So y of t is equal to 5 e to the negative kt. And so that's how we get, that's the whole point of these Laplace transforms. We can go from this form right here, from the differential equation, to the analytical solution. Let's go ahead and look at problem 3b now. We have d squared y of t over dt squared plus 2 dy dt plus y of t is equal to 5. We have the initial conditions that y dy dt and d squared y dt squared are all equal to 0. Let's go ahead and look at the Laplace transforms first. dy dt is equal to s f of s minus y0. This could also be a y, capital Y right here with this f of s. We also have dy dt squared is equal to s squared f of s y is naught minus the derivative at y naught. And where that comes from, let's just look right here. We have this function we used before, we have this function we just used, and we have this one right here, which is for the nth derivative is equal to, here we have a second, so s squared f of s, so s squared ys, minus s n minus 1, so s f naught, so s y naught, minus s to 0, so no, that's all going to be 1, f to the first 0, so that's going to be f prime. That's where we come up with that. So let's go ahead. We set our y naughts and our y's to 0, so we get s squared ys plus 2s ys plus ys is equal to 5 over s. This, I was going to start doing some parentheses. That's just a 5. Then we have ys is equal to 5 over s times s squared plus 2s plus 1. So ys is equal to 5 over s times s plus 1 squared. If we look at our table again, you'll notice right here, this is really what we have. We have, if tau is 1 and this zeta is 1, we have 1 over s times s squared plus 2s plus 1. So this is a second order system. As we come to these second order systems, we find the analytical solution is equal to y of t is equal to 5, 1 minus 1 plus t e to the negative t. And that's our analytical solution. This is a second order system is the whole point here. And again, we've converted from some complicated differential equation to some analytical solution. Finally, let's look at 3c. We're going to take this is actually a first order plus dead time, the same equation, this first order equation, and we're going to find the analytical solution for a doublet u of t and yt. The ut is the same step equation we had from problem 1, so 3 over s e to the negative s minus 3 over s e to the negative 5s. Then the function y. Tau is equal to, we look at the derivative here, that's sys minus y naught equals negative ys plus k times our u. So here our u is in the Laplace form. If we distribute this out, and we move the y's to the one side, we have y of s is equal to k over tau s plus 1. The tau is coming from right here, and the ys is coming from right over here, where that plus 1 is coming from. So we have tau ys plus 1 times 3 over s e to the negative s minus the same thing, except we have a different for that u function on the right hand side. Then we need to remember two things. The first is that, let's look at this table again. Right here is where we find that 1 over s times tau s plus 1 is equal to 1 minus e to the negative t over tau. The second is that we have some exponential right here, e to the negative tau naught s is equal to this step function right here, and then we offset whatever function we're multiplying it by this t minus tau naught. So we go ahead and we apply that in. Here's that t minus tau naught, and here's the t minus tau naught, and then the step functions you'll see right here. So it's y of t is equal to 3k 1 minus e to the negative. It would be t over tau, but it's t minus 1 over tau because of our step function. And then s, which is our step function, t minus 1. And then similarly, negative 3k. And then our step function is 5, so we have a 5 instead of 1 here and here. The last portion of our assignment then is to graph this function that we just derived. So we'll go ahead, I'll zoom out. What I've done, let me make it so we can see our code, is I create k is equal to 1, tau is equal to 2, subject to what we've been told. And I create a vector that goes from 0 to 8 and has 81 points. Our step 1 is our step function 1, where after 1 second it goes up to 1. And our step function 2 is our second step function, where at t equals 5 it goes to 1. Then we plug in our analytical solution. You'll notice the only thing that's kind of tricky here is that we have these dots anytime we do multiplication or division of matrices, so that we do it element-wise. But we have our 3 times k times 1 minus the exponent of negative t minus 1 over tau times the step function, and then minus 3 times k 1 minus the exponent t minus 5 over tau times the step function 2. And you'll see there's the output. And it looks like an FOPDT. At 1, we start rising, and then we start decaying at t is equal to 5. So there you go. Hopefully things made a little bit more sense, and hopefully this helped you identify how Laplace transforms can be used to help us convert differential equations into analytic solutions.